Alright, so here is lesson 7, common distributions. So just a review of the normal distribution. It's a bell-shaped distribution with a mean of 0 and a standard deviation of 1. It's also known as a z-distribution, and just know that 100% of your observations will fall under this normal curve. So the central limit theorem states that if your sample size is sufficiently large, then the sampling distribution will be approximately normally distributed. So just remember that your z-score, also known as your standardized score, is the difference between an individual score and the mean in standard deviation units. So when you're using the normal distribution for hypothesis testing, you go through a 5-step hypothesis testing procedure. So this is a little different from when you conduct a randomization test. So your 5 steps are going to be 1, check your assumptions and write your hypotheses. 2, calculate your test statistic. 3, determine the p-value. 4, make a decision. And then 5, put your decision from step 4 into a real-world conclusion back into the context of the original problem. So if your sampling distribution is approximately normal, then we'll construct a normal distribution, and your mean will be equal to the hypothesized parameter, which is the number in the null hypothesis. And then your standard deviation will equal the standard error, and from that you can find your p-value. So when using the standard normal distribution method, you can use this method, and the test statistic will be the standardized value, and you can use that to find the boundary of the p-value. So finding your z-score, you can calculate that by doing x minus x bar, and then divide that by your standard deviation. And then when you're conducting a hypothesis test, your sampling distribution is centered on the null parameter, and the standard deviation is known as the standard error. So you can calculate your test statistic from here by taking your sample statistic minus the null parameter, which is the number in the null hypothesis, and then divide that by the standard error. And then once you get your test statistic, you can use that to calculate your p-value. So we're going to go through an example of this with a proportion of Stat 200 students that are female. So the question is, are more than 50% of all World Campus Stat 200 students female? Data were collected from a representative sample of 501 World Campus Stat 200 students. In that sample, 284 students were female and 217 were male. So we're going to go through each of the 5 steps individually, and I have the prompt again there on the board. So step 1 is to check your assumptions and write your hypotheses. So when checking your assumptions is just making sure that your sample size is sufficiently large enough, for example, in order to conduct a hypothesis test in the first place. So we checked our assumptions, so therefore we can write our hypotheses. So our null hypothesis is that p equals 0.50. We use 0.50 here because we're checking to see if the majority of students, so a majority would be greater than 50%. So 0.50 is our hypothesized parameter, and our alternative hypothesis is p is greater than 0.50. So now we wrote our hypotheses, so we have to calculate our test statistic. So we can calculate p hat by taking 284, which is the number of female students in the sample, and dividing that by the total number of students in the sample, and we get 0.567 as our p hat. Then we use the hypothesized parameter and the standard error, which we got from the randomization distribution, to calculate our test statistic. So we take 0.567 and subtract 0.50, then divide that by 0.022, which is our standard error, and we get a test statistic of 3.045. So now that we have our test statistic, we can use that to determine the p-value. So we plug that into our normal distribution, and we find the area under the curve that is more extreme than our observed test statistic of 3.045. So after doing that, we get a p-value of 0.0011. So that's a very low p-value. And from that, we say that that is less than our alpha of 0.05. So we can reject the null hypothesis. So now that we rejected our null hypothesis, moving into step 5, we can say that there is evidence that the proportion of all World Campus Stat 200 students who are female is greater than 0.50. Okay, so moving into confidence intervals. So something to know with confidence intervals when you're using the normal distribution is that your mean is equal to the sample statistic, the standard deviation equals the standard error, and the confidence interval is in the middle of that distribution. So for example, for a 95% confidence interval, you find the middle 95% of that sampling distribution. So using the standard normal distribution method, we have that similar 95% confidence interval formula. So you take your sample statistic and you add and subtract 2 times the standard error. So that would be for a 95% confidence interval. The general form for a confidence interval is your sample statistic plus or minus z star times your standard error. So your z-star multiplier can be found in the z-distribution. So for example, for a 90% confidence interval, we would find the z-scores to separate the middle 95% of the z-distribution from the outer 10% of the z-distribution. Okay, so moving into binomial probability. So a binomial random variable is a specific type of discrete random variable that counts how often a particular event occurs in a fixed number of tries or trials. So in order to label something as a binomial random variable, it must meet 3 conditions. So it must meet all 3 of them. It cannot meet less than 3. It must meet 3 in total. So no exceptions. So the first variable condition it must meet is that there are a fixed number of trials or a fixed sample size. The second is that the probability of success must be the same on each trial. And the third is that trials are independent of one another. So an example I like to use for binomial random variables is the number of tails you get when you flip a coin 10 times. So if you go through the checklist, we can say that yes, there is a fixed number of trials. So we have 10 trials here. 2, the probability of success is the same on each trial because no matter if you flip heads or tails on the previous try, you still have a 50% chance the next try of getting heads or tails. So it's the same for each. And then the trials are independent of one another because the result from the second trial does not affect the result of the third trial. All right, so the mean of a binomial random variable, you can calculate this by taking your n and multiplying that by your p. And then you can also calculate the standard deviation of your binomial random variable. So here, we can calculate the number of red flowered plants, a binomial distribution, with your n is equal to 5 and your p equals 0.25. So we can calculate our mu here. We can do that by calculating, or by multiplying, your n times your p. So you multiply 5 times 0.25. And therefore, you get a mean for your binomial random variable of 1.25. And then also plugging that into the standard deviation formula, 5 times 0.25 times 1 minus 0.25. And then you just take the square root of that number, and you get 0.968. And then you can say that the mean number of red flowered plants when 5 plants are planted is 1.5, and that has a standard deviation of 0.968. Okay, so we're on to our first review question here. All right. So let's apply the empirical rule to determine the SAT math scores that separate the middle 95% of scores with n, 500, and 100. So choose your best answer here. All right. So we can go over this one now. So let's apply the empirical rule to determine the SAT scores that separate the middle 95% of these scores. So the answer here is B, 300 and 700. We get that because since we're finding the middle 95% of scores, we'll take our mean of 500 and then add and subtract that to 2 times 100. So we use 2 here because that is the multiplier we use for 95% confidence interval. And then we use 100 because that is our standard error. So once we add and subtract that out, we get 300 and 700 as our final answers. All right, so moving on to question 2. The central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed for many frequently tested statistics. True or false? All right, so this statement is true because this is the definition of the central limit theorem. So if your sample size is sufficiently large, then your distribution will be approximately normally distributed. All right, moving into the third question here. So which of the following is not an example of a binomial random variable? All right, we're going to go over that here. So our answer here is B, the number of winning lottery tickets when you buy 20 tickets of a different kind. So A, C, and D are all examples of binomial random variables because they fit all three conditions that I listed below in the bottom. B does not fit one of those conditions, so we'll go through them. So starting with the first condition, yes, there are a fixed number of trials. There are 20 trials here. And then 2, the probability of success is the same on each trial. That is not true in this case. Since we have different kinds of lottery tickets here, the probability of success varies for each lottery ticket that you buy. And then finally, the trials are independent of one another. Yes, that does vary because it doesn't matter what your result of one lottery ticket is, it will not have an effect on the other lottery tickets that you check. All right, now this is our last question here. In a very large class, each student flips a fair coin 10 times. The number of tails that each student observes is recorded. Compute the expected mean of that distribution. All right, and we're going to go over that here. So here our mean is 5. To calculate that, we go through that formula again. So mean equals our n times our p. N is 10, p is 0.50. We multiply those two together. 10 times 0.50 is 5. So that's our final answer.